Today we're going to be looking at 3.9 and section 4.1, or an intro to section 4.1, and all of this will also be on our chapter 3 test. So the idea that we sort of talked about a little bit in a previous day's notes was using tangent lines to approximate function values. So the idea is this: the graph of a function could be approximated by a straight line that is tangent to the function. And depending on how close you are to that point of tangency, the linear approximation could be fairly close to f of x. But then, of course, you can see the further out you get from A, the more distance there would be between the linear approximation and the actual function value. The only place that they would be exactly the same is at that point of tangency. And we talked about previously that second derivative test to help us find relative max or min. We also made a quick note in that packet of notes that said, if your function is concave up at a certain point, then the tangent line will underestimate the value of the function, the actual value. And if the function is concave down at your point of tangency, then the tangent line approximation would overestimate whatever the actual function value is. Because you can see in either case, the tangent line would be above where the actual function value is. So find the tangent line approximation of f of x equals 1 plus sine x at the point 0, 1. So finding the tangent line approximation is not finding a numerical value, it's finding the tangent line equation, and the point of tangency is 0, 1. And then use a table. I've already filled it out for you because I didn't want to take the time to do that, but use a table to compare the y values of the linear function to those of f of x. So ignoring this table for a second, let's find the tangent line approximation. We have a point already. To write the equation of a line, we need a point and a slope. So I need to find the derivative of f of x and then evaluate it when x equals 0. So the derivative of 1 is 0. The derivative of sine is cosine x. And evaluating the derivative when x equals 0, cosine of 0 is equal to 1. So our tangent line approximation, now normally we would use point slope form, right? Y minus 1 equals 1 times x minus 0, but the point 0, 1 is a y-intercept. So it's probably worth just simplifying this or getting straight to y equals x plus 1. This is the tangent line, and we would be using it to approximate values near 0. We don't need to approximate the value at 0 because that's the point of tangency. And so that's the one point that is exact. But anything beyond 0 will give me different values. So if you take a look at this table, the top row is plugging in these various values near 0 for x and getting the, we'll call this the quote-unquote actual value. These are still approximated because they're rounded, but whatever. So plugging those in and then plugging the same x values into your 1 plus x equation, approximation. And you might notice, so to the left of 0, all of these points, the approximation is just slightly less than the actual function value. So I'm going to write approximation less than actual. And then, of course, they're the same at the point of tangency. But then over here to the right of 0, the tangent line approximation is slightly bigger than the actual value. So the approximation is actually greater than the actual. Now, back here we said, at our point of tangency, your graph could be concave up or concave down. Well, here the point of tangency will have to be a point of inflection, because if the approximation is less than the actual, that means that we've got this sort of situation going on this side of 0. And if the approximation is higher than the actual, we've got a concave down situation going on to the right. If you think about the graph of 1 plus sine x, normally the sine x graph would start at 0, do one of these, right? If If you shift it up one, it looks like this, something like this. There's one period of the sine graph. If you go to the left, something like this. Okay, so yeah, so at 0, this 1 plus sine x graph, it does switch from concave down on the right, concave up on the left. And so at 0, that is a point of inflection. So that is why, depending on which side of 0 that we're on, depending on which side of the point of tangency that we're looking at, the approximation changes from being an underestimation to an overestimation. Now that only happens if the point of tangency happens to be a point of inflection. So number 2, find the local linearization. That is just another way to say tangent line approximation of the function f of x equals tangent x at the point pi over 6, 1 over radical 3, and then use your equation to approximate the tangent of 9 pi over 48. Then compare this value to the actual value. We're going to put that in quotes because we're going to use our calculator, which is going to still approximate a value for tangent of 9 pi over 8. All right, so let's find the tangent line equation first. We need to find the derivative of tangent x, that's secant squared x. We need to evaluate the derivative at the point of tangency, which is when x equals pi over 6. And I don't think well in terms of secants, but I do think pretty well in terms of cosines. So I'm going to think to myself, what is the cosine of pi over 6? I should do 1 over the square of that value. All right, so cosine of pi over 6 is radical 3 over 2, and we're squaring that. So 1 over radical 3 over 2 squared. That's 1 over 3 over 4, which is really 4 over 3. Right? So that's our slope. Our point slope equation would be y minus 1 over radical 3 equals 4/3 times x minus pi over 6. And since I am going to be plugging in for x and getting a y value, I think I would like to at least add this over. I'm not really going to distribute because we're going to be using a calculator for this one so that we can compare the actual value. So the approximation, that would be tangent, I would write it like this, tangent of 9 pi over 48. You want to show that it's approximately equal to the little squiggly equal sign. And then I would just show that I'm plugging in 4/3 times 9 pi over 48 minus pi over 6 plus 1 over radical 3. So I'm going to go to my calculator and give the decimal approximation for that. If they're asking you to compare to an actual value, chances are pretty good that this would be a calculator question. All right, so let's see it. All right, so that was 4/3 times. I know I can simplify some of this typing by getting common denominators, but if we have a calculator, why risk making a mistake? Okay, so I'm going to write this to more than 3 places so we can see if they're close, how close they are, to how many decimal places they're close. 0.664616737 This is the approximation, and the actual value would be plugging in 9 pi over 48. We're saying actual in quotes because when you type this into your calculator, it's still cutting off this decimal. So they're the same to 2 decimal places, and then they go off after 3. So I'm going to write this down to the same amount of places, 0.668178637 right? And then there's a follow-up question here. It says, which is greater, the tangent line approximation or the actual value? So 0.664 is smaller than 0.668. So I'm being very informal here. Actual is larger. What conclusion can you make about the curve at x equals 9 pi over 48 and y? So since the actual value is larger, I always think in terms of the approximate. If the approximate is lower than the actual, it means that you must be concave up because you might be sitting here. The approximate is sitting here on the line, which is below the actual. Okay, so what can we say about the curve f of x? We can say f of x is concave up at x equals 9 pi over 48 because the approximation, I'm going to abbreviate, is less than the actual at this value. What conclusion can you make about the sign of the second derivative evaluated at 9 pi over 48? So if we know that f of x is concave up, it means that the second derivative at 9 pi over 48 must be positive, so greater than 0. And it says why, so I'm going to say because f of x is concave up. Now, you wouldn't have to keep going like, if these were parts to an AP question, you wouldn't have to answer again why you know that f of x is concave up. You don't have to over-explain. Now, this second page here is your part of your homework for tonight. So work on these practice problems and then check your answers with my complete key, which is in the notes section, chapter 3 notes section. All right, now we're moving on to intro to chapter 4, antiderivatives. We are going to start talking about antiderivatives a little bit. No major integration going on our chapter 3 test, but this content is on our chapter 3 test because it relates to what we've been doing. All right, so these two problems are similar to old AP questions, not exactly the same. An object moves along the x-axis with, this should not say initial velocity position x of 0 equals 2, because if it were an initial velocity, we wouldn't say the word position, and it would say v of 0 equals 2. It means initial position, x of 0 equals 2. The velocity of the object at time greater than or equal to 0 is given by this velocity function. What is the acceleration of the object at time 4? It would be good to note on an AP test as a way to kind of prove or show your work. A of t, acceleration, is equal to the derivative of v, so v prime of t. That's not required, but it's kind of a nice organized way to show what you're doing. And then I would take the derivative. Now remember, you've got a chain rule going on. And rather than write this out in 2 steps, you want to start getting into the habit of being able to take simple chain rule problems and write them in their final form. So instead of saying cosine of pi over 3t times pi over 3, I would like you to get to a point, if you can, where you just write pi over 3 cosine of pi over 3t. If that's too much, if you don't like it, you can do it in 2 steps. It's just, we're trying to be efficient and not clutter our work and all of that stuff. So this is A of t. We're supposed to evaluate the acceleration at t equals 4. So I'm going to say A of 4 equals, I should show my work, pi over 3 times the cosine of, if you put a 4 in there, that's 4 pi over 3. That's pi over 3 times, so cosine of pi over 3 is 1/2, and you're in quadrant 3. If you're talking about 4 pi over 3, cosine's negative in quadrant 3, so negative 1/2. So A of 4 is equal to negative pi over 6. And we don't have units in this problem. You don't have to write, it would be units per, time unit squared, but they're not going to make you write that out. So, but in general, acceleration is like, if this were inches per second squared, it's inches per second, so you would write inches per second squared, just FYI. Consider the following 2 statements. Statement 1, for t between 3 and 4.5, the velocity of the object is decreasing. And then statement 2, for the same time frame, the speed of the object is increasing. Okay, so velocity is change in position over time, and speed is not supposed to have a sign, right? It's just how fast are you going. Are either or both of these statements correct? For each statement, provide a reason why it is correct or not correct. So for statement 1, now let's assume we're not told that this object moving along the x-axis has any discontinuities, so let's assume continuous differentiable everywhere. Actually, you know what? We don't have to assume that because the velocity function is continuous. So that tells me that there wouldn't be any points where our position is discontinuous. So is velocity decreasing? Well, we evaluated the acceleration at 4, the derivative of the velocity at 4, which is in the middle of this, or somewhere within this interval. So I can say a of 4 is negative, less than 0. Therefore, 3 little dots in a triangle mean therefore. Therefore, v of t is decreasing. I'm going to say on the interval. It's at t equals 4, but again, if this is a continuous function, then it would be decreasing on this interval. So on 3 to 4.5. So we're supposed to say correct or incorrect. Velocity is decreasing, yes, because acceleration is negative. So I'm just going to say correct. And then statement 2. Is the speed increasing? Just in general, remember that speed is increasing if velocity and acceleration have same sign. Meaning, if your velocity is decreasing, your acceleration needs to be negative. So your change in position is decreasing at a certain velocity. So you're going, you're falling and you're accelerating in that negative direction. It's pushing you faster in that negative direction. Speed would be decreasing if they're working against each other. So you're falling, but the acceleration is pushing you upward, like a parachute type thing. All right, so is the speed increasing? Well, we know that the acceleration is negative at 4, but we haven't evaluated the velocity at 4, so we should find v of 4. V of 4 is the sine of 4 pi over 3. We were given that function back here. Sine of 4 pi over 3, the numerical value doesn't matter, but we should know sine of pi over 3 is radical 3 over 2. In the third quadrant, that's negative radical 3 over 2. And so, since a of 4 is less than 0 and v of 4 is less than 0, the speed, they have the same sign, so the speed is increasing. So, that statement is correct. All right, number 2. Particle moves along the x-axis so that its velocity at any time greater than or equal to 0 is given by this function. Write a polynomial expression for the position of the particle at any time greater than or equal to 0. Now, we haven't talked about integrals. I know some of you have worked with integrals in physics class, or if you had AB last year, but don't think about anything like that. Just think the position. The derivative of the position would be the velocity. So if you just take this basic function right here, think about what would the terms have to have been to get a derivative of 3t squared. So, and since we're moving along the x-axis, let's make this x of t. So the first term should be t to the third, right? Because the derivative of that would be 3t squared. Minus, if the derivative is 2t, it would have been t squared to begin with. Minus 1 would have been minus t. And you can double check, if you take the derivative of those 3 terms, do you get 3t squared minus 2t minus 1? Yes. This says write a polynomial expression for the position of the particle at any time 0. So this is a possibility. Could there be more than one answer? Explain. Yes. What if I would have done this? Same first three terms. What if I put a plus 10 on the end? When I take the derivative of this function, I still get the velocity equation because the derivative of 10 or any constant that I add or subtract here is 0. So it's not going to show up in that velocity equation. So my explanation is any constant can be added to the position function. And we would still get that same velocity when we took the derivative. Now part C says, given the position x of t equals 5 for t equals 2, write the position equation for any time t. So once you're given an official position that has to work in your equation, there are no longer an infinite number of answers for your position function. Now there should only be one correct answer. So we would set that up like this. Instead of putting a plus 10 on the end, I could have said that the position function has to be t cubed minus t squared minus t plus some constant, we'll call it plus c. And then we know that when t equals 2, so subbing 2 in for all these t's, 8 minus 4 minus 2 plus c, when t equals 2, x of t equals 5. So that equation, position equation, is equal to 5. And we can use that to solve for c. So 4 minus 2 is 2. 5 equals 2 plus c. So c equals 3. Once you find the constant that needs to be added to your position function to make this relationship true, then you have your answer for the position function. X of t has to equal t to the third minus t squared minus t plus 3. That is the position function for which we would have this velocity function, and the position 2, 5 actually works. For what values of t between 0 and 3 is the particle's instantaneous velocity the same as its average velocity on the closed interval 0 to 3? Average velocity was chapter 1. Average velocity. Remember, that's change in position over change in time. So it is x of 3 minus x of 0 over 3 minus 0. All right, so the average velocity, when you plug in 3 into the position function with plus 3 on the end, you'd get 27 minus 9 minus 3 plus 3 minus, when you plug in 0, 3, and then it's all divided by 3. Okay, so 27 minus 9 is 18, and then these 3's cancel themselves out. 18 minus 3 is 15 over 3. So I get an average velocity of 5. Now I need to know, when is the instantaneous velocity for what values of t? When is that equal to 5? So I go back to my velocity equation, wherever it went, there it is, and set it equal to 5. 3t squared minus 2t minus 1 equals 5. Get this equal to 0. We might try a little bit to factor it, but you should quickly find out that it does not factor, but it's quadratic, so we can solve using quadratic formula. And I'm sure this simplifies, so let's see, square root of 4 plus 12 times 6. 4 plus 72 is 76. And then how does that simplify? Let's see, 4 goes into that, so I can pull a 2 out. 4 goes into that once, 9, so 2 radical 19. 2 plus or minus 2 radical 19 over 6. And then be careful. We're only on the interval 0 to 3. The 2 minus 2 radical 19 is going to be negative because 2 minus 2 times something is negative, if that something is bigger than 1. So I can divide everything by 2, but I shouldn't have the plus or minus in my answer. I should only have the plus. So 1 plus square root of 19 all over 3. That would be my exact answer. Find the total distance. Again, remember in chapter 1, I think it was, total distance meant we had to make change in positions positive no matter what. Travel by the particle from time 0 to time 3. If this is a no calculator problem, then we need to figure out where that change in position is negative. So in other words, where does this particle turn around? It's going on the x-axis. When it's moving to the right, its change in position is positive, but does it turn and go left at any point? The particle would turns around when v of t changes sign, right? Because when v of t is positive, the particle's moving right. When it's negative, the particle's moving left. So I should set the velocity function equal to 0 and see if I can solve that. So the velocity function was 3t squared minus 2t minus 1. Now that does factor. And we get 2 times negative 1/3 and 1. Now negative 1/3 is not on our interval though. Remember, we're only 0 to 3. 1 is on the interval. So at 1 second, the particle is changing position. I can figure out if I want to whether it's moving left or right, but that doesn't really matter. Basically, all you need to do is figure out, you could put an absolute value no matter what, but you could say, I need the absolute value of the change in position between 0 and 1 second, so like x of 1 minus x of 0, and just force that to be positive by putting an absolute value around it. And then I want to add to that, again, forcing this positive whether I need to or not. I need the change in position from 1 to 3, which is subtracting x of 3 minus x of 1. And that would be the total distance. All right, so x of 1, I don't know that we've plugged that in yet. That would be 1 minus 1, so nothing. And then negative 1 plus 3 is 2. Minus x of 0 is 3. So that's the one that we really needed this absolute value for. So 1 unit change right there. And then x of 3, we had figured out back here. That's 18 and then minus 0. So that's 18. Minus x of 1, we found out before, was 2. Now, you didn't need absolute value around that, but it's not wrong to write it. It's fine. We needed that turning point to know how to split this up. So 1 plus 16 is a total distance of 17 units. Again, we don't have any actual units like centimeters or inches or anything, but that would be the total distance. Now, in a couple of days, we're going to talk about antiderivatives and integrals, and you'll be able to do the same thing where ultimately we want the integral of the absolute value of the velocity, but I don't want to talk about that quite yet. But you could check that on your calculator if you know what I'm talking about, and the calculator will get very close to 17 with some extra decimal places carried out. This is the rest of your homework for tonight. Finish this page. All right, that should be it for today. Make sure you check your answers to these 2 pages that you had for homework in my notes folder. I won't have it linked separately in the homework. And please email me or come to office hours if you have questions.